Now let's see not denote a circle. Yeah, you can see this figure here. C naught is a circle given by this. Absolute value of G is equal to R0. Its orientation is clockwise. Yeah, so must be careful because we consider the point at infinity. We should consider this direction clockwise direction. Yeah. So where R0 is greater than R1 here. R0 is greater than R1 here. The residue of f at infinity is defined by means of the equation 1 here. Integral along to control C naught f of g dg is equal to 2 pi I times residue of f of g at point at infinity here. Here, note that the circle C0 keeps the point at infinity on the left. Yeah, infinity there. There exists. Yeah, the point at infinity on the left side. On the left, when we consider the direction of the circle C naught C0, because the direction indicate this. So infinity, point at infinity is on the left side. We do similar things, just at the singular point in the finite plane, equation 3. Do you remember? Yeah. Here, if you look at this figure, with that figure, okay, same figure, okay. Then we consider this direction, which is oriented in the counterclockwise direction, and then the contour contains singular point inside this. So when we consider the direction of this contour, the point is placed on the left. So we have the same condition for the point at infinity here. So the reason we consider the clockwise direction here. Then since f is analytic throughout the closed region bounded by C and C0, okay, we applied the principle of deformation of paths, which is described in section 63. So we get this result here. Integral along to control C, f of g dg is equal to integral along to control negative C0, f of g dg. And then we can rewritten this into this by pulling out the negative sign outside integral. So we get this. And we have the definition 1 here for the residue of f at infinity. So this part can be replaced with this 2 pi I times residue of f at infinity. Then we get this result, equation 2. Okay, we need to find the residue. We consider the Noran series. In section 66, we have this formula here, where the region throughout that f is analytic is given by this. The absolute value of g is greater than R1 and less than infinity here. And n moves from negative infinity and to positive infinity, the term is given by this, where the coefficient Cn can be computed by this 1 over 2 pi I times integral negative C naught f of g dg divided by g to the n plus 1 here, and moves to n plus minus 1 and plus minus 2, keep going like this, which means n is a integer. Then we replaced g here by 1 over g and then multiply through the result by 1 over g squared. Then we get this 1 over g squared times f of 1 over g is equal to summation n is negative infinity to infinity Cn divided by g n plus 2. We can easily this result from this, and then modify something without actually any modification, but expression. Here we modify Cn to Cn negative 2, and we cancelled g squared in the denominator here. Then we get this reason because we replace g by 1 over g here. Then we get this. When g goes to infinity, 1 over g, close to 0, and g move to r1, then we get 1 over g, close to 1 over r1. So we get this region. And the c negative 1 is 여기 here. C negative 1 is equal to residue of 1 over g squared times f 1 over g at point g is equal to 0. In expression 4 here, by insert here 1 for the n, then we get this c negative 1. So we have the result. C negative 1 is 1 over 2 pi I times integral negative c naught f of g dg, or another expression, another result, integral c naught f of g dg is equal to negative 2 pi I times residue this function at the point g is equal to 0. Now and this result and definition 1 here, definition. So we get equation 6, the result, residue f of g at point, residue of f at point at infinity is equal to negative residue g is equal to 0 of residue of 1 over g squared times f of 1 over g at point g is equal to 0. So with equations 2 and 6, 2 is here, and 6 here, the theorem theorem is completed, because theorem says that we have the result this here. Oh, this result. Sorry. Yeah, this part is equal to this, and this part equal to this. So this part is same with this. So replace it by this, then we get this result here.